Hello, 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 and welcome back to Shiksha DaCosta. Today we are going to be learning about theoretical probability. This is part of our unit on applying probability to our own daily lives. So in this lesson, we're learning what something called theoretical probability is. We're learning how to calculate it, and we're learning how to find it using something called a tree diagram. And you're successful when you can determine what is the theoretical probability of an event, and when you can represent that probability in a variety of ways. So to start off, I'll ask you these two questions, and take 5 minutes here. You can go ahead and pause the video and think about these and see what your answers are. What is the probability that you get heads when you flip a coin? That one's kind of easy, but then the next one gets a little bit tougher. What is the probability that you get heads once and tails once if you take that same coin and you flip it twice? So hopefully you were able to think about that for a bit, and you realize that there are three ways of coming up with this answer, three ways of expressing it. The first thing to do is realize, well, how many different outcomes can happen if I flip this coin? And there are two. There's just heads and tails. And so I've expressed that here with a little probability space, right? I made a little rectangle, I've cut it into two pieces, two equal pieces, and I've said one is H and one is T. Now, what is the probability that you get heads? Which means if we're looking for a heads, there's only one outcome that matches our criteria. And that's this one right here, heads. If we get tails, that doesn't match what we want. And therefore, the probability can be expressed as 1 out of 2. 1 out of 2 possible outcomes matches our criteria. If we take 1 and divide it by 2, that gives us 0.5. So this is a fraction. 1 over 2 expressed as a decimal would be 0.5. And then expressed as a percentage, we just multiply it by 100 to get 50%. So there are three different ways of expressing the probability of getting heads when I flip a coin. 1 over 2, 0.5, or 50%. And of course, those are using numbers. There's also this fourth way, which is a probability space. What about this question? What is the probability that you get heads once and tails once if you flip that coin 2 times? One way to answer this question would be to go back to this idea of probability space. So in this case, we took this probability space and we broke it up into two pieces, one getting heads and one getting tails. Well, if we flip this coin a second time, then, if we got heads the first time, now there's two different outcomes that you could get for the second flip. So the first time we flipped it, you could get heads or you could get tails. But now if we're only in this part, so if we got heads the first time, then we would need to split this probability space up into 2 to show that the second time could be heads or it could be tails. And so this heads, if we flip the coin a second time, if we got heads the first time, now there are two outcomes, heads or heads and then tails. Similarly, we could take the tails outcome and do the same thing. We could either get tails and then heads or tails and then tails again. So now there are actually 4 different outcomes, right? You could get 2 heads, heads and then tails, tails and then heads, or tails and then tails, 2 tails. And my probability space for something like this would maybe look like this, where this is the probability. These are all the different things that could happen, and I've split it up into 4 equal pieces because all 4 outcomes are equally likely. Heads, 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 tails, tails, heads, or tails, tails. Now, which of these matches our criteria? When we examine our probability space, we can see for sure that if we get heads and then tails, that matches our criteria. But if you look closely, you'll also notice that I didn't say heads first and then tails. I said heads once and tails once. And getting tails and then heads still matches our criteria. So there are actually 2 outcomes that match our criteria. The probability of getting 1 heads and 1 tails is 2 out of 4. And that reduces to, if I do 2 divided by 4, to 0.5, which is the same as multiplying by 100, 50%. So there's a 50% chance that you get 1 heads and 1 tails if you flip this coin 2 times. Now you notice that the answer in both of these was 50%. I guess a question that might come to you is like, is the answer ever going to not be 50%? And certainly, one question that you could ask, maybe you could pause the video here and think about, what's a question that you could ask where the answer would be something other than 50%? And hopefully you get to see, just looking at the probability space, you could ask, what's the probability that you get tails twice? And this is the only outcome that gives you tails twice. So there's 1 outcome out of 4, which would be 25%. So in today's lesson, we're going to be learning about probability in this way. When something happens that seems like it would be really rare, one of the questions that we ask ourselves very, very often is like, oh my God, what were the chances of that? This must seem so unlikely. And this is especially true when in order for this thing to happen, there were several really rare events to occur. When I was in high school, I had a teacher who had 7 children, all boys. And we were asking ourselves, oh my God, what is the chances of having 7 kids and no girls? So this is a question that we naturally ask ourselves all the time, right? In order for that to happen, that teacher would have had to have a boy 7 different times. There were 7 different chances to have a girl, and in each one of those he had a boy. That's one of the things that makes us ask this question, when there are several events that need to occur for our outcome. To help us understand situations like this, we can use something called a tree diagram. This helps us to illustrate or to show us visually all of the different outcomes that could happen in a situation. In a tree diagram, this is how you do it. You write all of the different outcomes for the first step. Then for each of those outcomes, you draw a line to each outcome of the next step. So in our example previously, we had heads and tails. That was the first step. And then for each of those, we drew a line to the heads and tails of the next step. And we continue this, even if it's more than 2 steps. And it sort of starts looking a bit like a tree growing. And then we write the final outcome for each branch. What were all of the things that happened in that branch? And of course, I'm going to demonstrate this with an example. What are the chances of rolling a 10 with 3d4? What does 3d4 mean? It means 3 dice that each have 4 sides. So with each of these special dice, notice that you could roll a 1, you could roll a 2, a 3, or a 4, depending on which side of the tetrahedron, this triangle-like shape, depending on which point is pointed up, that's the number that you've rolled. What are the chances that you roll a 10 if you roll 3 4-sided dice? Now, what does it mean to roll a 10? None of these dice can give you 10 by itself. In fact, even 2 of them would not be able to give you 10. But if we have 3 of them together and we rolled all 3 and added up the numbers that we see at the top, maybe we could get a 10. Well, to look at a situation like this, whenever we have several events happening, we always look at, okay, what are all the different outcomes for if I rolled these 3 dice? What are the different outcomes I could get for the first dice that I roll? So I'm going to look at the blue one. I could get a 1, okay? And if I do get a 1, what are all the different outcomes for the second dice? I could get a 1, a 2, a 3, or a 4 for the second dice. And notice I'm connecting these with lines, like little branches, to show that, okay, I rolled a 1 with the first dice, then I rolled a 1 with the second dice. And if I was in that situation where I rolled a 1 and a 1, what are all the different numbers that I could roll with the third dice? You may be thinking, oh, I rolled a 1 2 times. Maybe I'll be more likely to roll a 1 here, but that's not true. This dice is totally independent. It could still roll any number from 1, 2, 3, or 4. And similarly, if I rolled a 1 and then a 2, the third dice can still be 1, 2, 3, or 4. A 1 and a 3, same situation. A 1 and a 4, same situation. So these are all the different outcomes if I roll a 1 on the first dice. But of course, I don't have to roll a 1 on the first dice. I could roll a 2. And that would have 4 different outcomes for the purple dice. And then for each of those outcomes, 4 different outcomes for the red dice. I could also roll a 3 on the blue dice. And that would again have 4 different outcomes for the purple dice. And for each outcome, 4 different outcomes for the red dice, 1, 2, 3, or 4. And finally, the last outcome for the blue dice is a 4. And if I roll that, I could roll a 1, 2, 3, or 4 on the purple. And for each of those, a 1, 2, 3, or 4 for the red dice. Now, the truth is, for tree diagrams, I would have all 4 of these, 1, 2, 3, and 4, these blue dice, all like closer together. But when your tree diagrams start to get a little bit bigger and bigger, you may have to separate them out like this, just so that you have enough space to write them all. Okay? But what does this tree diagram mean? It means that there are so many different outcomes. There's 4 outcomes for the blue dice, and for each of those outcomes, there's 4 more for the purple dice. And for each of those outcomes, so there's 4 times 4 is 16 different outcomes in total for 2 dice. For each of those, there's 4 more from the red dice. So 16 times 4 gives us a total of 64 outcomes. Now, let's look at what these outcomes actually are. Take a second to think about what is the total roll for each outcome. So let's start off with this one, just following this line from here to here to here. What would that total outcome be? This would be a 3, because we got a 1 on the blue dice, a 1 on the purple dice, and a 1 on the red dice. 1 plus 1 plus 1 is 3. The second outcome here would be 4, because we got a 1, then a 1, and now we got a 2. The third outcome would be a 5, 1 plus 1 plus 3. The next outcome would be 6, 1 plus 1 plus 4. What would this outcome over here be? This one would not be 7, like we're continuing a pattern here. Remember, it's 1 plus 2 plus 1, and that would be 4. Then the next one would be 1 plus 2 plus 2 is 5. 1 plus 2 plus 3 is 6. Then 7, and then 1 plus 3 plus 1 is 5. 1 plus 3 plus 2 is 6. Then 1 plus 3 plus 3 is 7. 1 plus 3 plus 4 is 8. Continuing on, 1 plus 4 plus 1 would be 6. 1 plus 4 plus 2 is 7, 8, and then 9. And I could keep going with this to fill out my entire tree diagram. 2 plus 1 plus 1 is 4. 2 plus 1 plus 2 is 5, and so on and so forth, right? I can fill out my entire tree diagram with all of the different outcomes from rolling 3 dice. These are all the outcomes. There's 64 of them. So there are 64 possible outcomes. What are the chances of rolling a 10? Think about this for just 2 minutes and see if you can come up with your answer. And again, how did I get this number 64? There are 4 different outcomes for the blue dice. For each of those, there's 4 outcomes for the purple dice. So 4 times 4 is 16. And then for each of those, there's 4 outcomes for the red dice. So 16 times 4 is 64. There are 64 possible outcomes. But what are the chances that you roll a 10? Again, think about this for just 2 minutes. So just looking at all of my combinations, I can see that there are 6 different outcomes that have a 10. I could roll a 2, then a 4, then a 4. I could roll a 3, then a 3, then a 4. A 3, then a 4, then a 3. a 4, a 2, and a 4, a 4, 3, 3, or 4, 4, 2. These are the only 6 outcomes that give me a 10. And 6 out of 64 is 0.09375, or as a percentage, 9.375%. Notice I did not do 10 divided by 64. Even though I'm looking for an outcome of 10, this number up here is how many of the outcomes match my criteria. And there are 6 of them that match my criteria. So I'm not going to do 10 divided by 64. I'm always dividing the number of outcomes that match divided by the total possible outcomes. So now just looking at this tree diagram for a bit, I want us to just, take some time to examine it and try to get our brains, which are really just pattern recognition machines, to see if we notice any patterns in this diagram. Take 5 minutes here to just look at it and think about it and see what you notice. One thing you might notice is that in these groups, to get to the next group in this vertical column here, these 4 numbers, if you add 1 to all of them, you would get these 4 numbers. If you add 1 to all of these, you would get these 4. And if you add 1 to all of those, you get these 4. So what might make that happen? What might cause that to actually happen? And if we look over here, we would see the only difference between this number, the first number in each of these rows. Let me just highlight these for us. The only difference between these 4 numbers is the purple dice. All of these is 4, 1, and 1, 4, 2, and 1, 4, 3, and 1, 4, 4, and 1. So the purple dice is increasing by 1, which is causing all of these 4 numbers to increase. You might also notice that horizontally, something like that happens as well. This is like 3, 4, 5, 6, and this starts at 4, 5, 6, 7. These 4 numbers are 1 more. These 4 numbers are 1 more. The reason for that is that the blue dice is changing each time here, right? So we're going 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 1, and that's why this number is increasing by 1 each time, is because we're increasing the blue dice by 1 each time. You might notice some numbers like 7 and also actually like 8, you might notice this as well. There's something weird happening here where like the first column has 3 7s and then 4 7s and then 3 7s and then just 2 7s. And if you notice, something kind of similar happens with 8s. There's 2 8s and then there's 3 8s and then there's 4 8s and then there's 2 8s. And I wonder if that pattern might hold up for any other numbers here, like let's say 4. There's 1, 2 4s, and then 1 4, and then none over here. Or what about 6? There's 1, 2, 3, 4 6s, 1, 2, 3 6s, 1, 2 6s, and then 1. So it goes 4, 3, 2, 1. So it's almost like, the middle, like the numbers seem to have a maximum of 4, which is, makes sense that, that number appears 4 times because there are 4 groups here in each column. But it seems like the number grows and then goes back to being small. Some numbers like 6, they only continue being small. Some numbers like maybe 10 only grow. There's 1 10, 2 10s, 3 10s. So they seem to only be getting bigger and bigger. I wonder which number, just thinking about that, which numbers are the most common? In other words, if we were rolling 3d4, which sorts of numbers would we be likely to roll? And that's actually going to be the second part of this investigation. Before we get to that, I do want to talk about another way to represent this probability. it's not just a tree diagram that we can rely on. We can also use that idea of probability space. So if I were to draw a square, inside the square, the area of this square is all the different possibilities, all the different numbers that we could possibly roll. And when we roll this blue dice, just like we split up that heads or tails, that probability space, into 2 pieces, we're going to split this up into 4 equal pieces because of the blue dice. So this is like rolling a 1, a 2, a 3, and a 4. And then each of these gets split up into 4 because of the purple dice. 1, 2, 3, and 4, right? So that's like rolling a 1, a 2, a 3, and a 4 on the purple dice if we were already in this space because we rolled a 1 on the blue dice. We could be in this space where we rolled a 4 on the blue dice, and then you could also roll a 1, a 2, a 3, or a 4 on the purple dice. Okay, and that would land us in one of these 4 spaces. And then for each space that we land in, again, we have to split it up into 4 because of the red dice. So if we do this for all of these squares all together, how many total different outcomes will we see? Well, this is 8 times 8 is 64. This is another way of imagining how we get our total number of outcomes. Is we're splitting up that probability space, and every time we split it, we multiply the number of different outcomes by how many pieces there are. So the first time there were 4 outcomes, then we split each of those into 4, so 4 times 4 got us 16, and then for each of those 16 we got 4 new outcomes. We split it up into 4 pieces. So 16 times 4 would have gotten us 64. So I might say that this square right here is like rolling a 1 on the blue dice, a 1 on the purple dice, and a 1 on the red dice. So this square right here is like getting a roll of 3. Whereas this square over here would be like getting a 4 on the blue dice, a 4 on the purple dice, and a 4 on the red dice for a total of 12. So going back to that question, what numbers would be the most common to appear in this tree diagram? To help myself out with that, I'm going to make a frequency table. So these are all the different outcomes I can get. Notice that I could not, even if I wanted to, I could not roll a 1 or a 2. The lowest number I can roll is a 3. And that's getting a 1 and a 1 and a 1. How many 3s appear in this entire tree diagram? Just one, just the one right over here. And so the frequency is 1. There's only one outcome that gives me a 3. I'd like you to take 3 minutes and pause this to fill out this table here, this column. How many times do you see each number appear? When I look at the number of 4s, there's 1, 2, 3 4s. There's 3 ways to roll a 4. And there's 1, 2, 3, 4, 5, 6 ways to roll a 5. There are also 10 ways to roll a 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 12 ways to roll a 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are also 12 ways to roll an 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 10 ways to get a 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And like we saw earlier, there were 6 10s, right? 1, 2, 3, 4, 5, 6. There are only 3 different ways to roll an 11. 3, 4, 4, 4, 3, 4, or 4, 4, 3. And there's only one way to roll a 12. So this is the frequency that these numbers appear. Notice that these are all of the outcomes. So if we add all of these up, we will get 64 total different outcomes. The probability of rolling each of these can easily be found then. Remember, the way we find probability is we take the frequency of that outcome, the number of times that outcome appears, and we divide it by the total. And if the total is 64 outcomes, to find the probability of rolling a 3, all we do is take 1, because that's how many outcomes match the roll of 3, out of 64. Similarly, the probability of rolling a 4 is 3. There's 3 different ways out of the 64 different ways to roll these dice. What's the probability of rolling a 5? There's 6 different ways out of 64. What's the probability of rolling a 6? There's 10 different ways out of 64. The probability of rolling a 7 is 12 out of 64, because there's 12 different ways we could get a 7. For an 8, there's also 12 ways to get an 8. There's a 10 out of 64 chance to roll a 9, a 6 out of 64 chance to roll a 10, like we talked about, a 3 out of 64 chance to roll an 11, and only a 1 in 64 chance that we roll a 12. To find the decimal version of these, we can just divide all of these numbers. And then when we want to convert those to percentages, we just multiply all of these numbers by 100. And that will give us 1.5625% chance to roll a 3. That's the lowest. A 3 and a 12 are the most rare. There's only a 1.5% chance, approximately, to roll those numbers. There is an 18.75, almost 19% chance that we roll a 7 or an 8. Those numbers are way more likely to roll. So now that we actually have a frequency table, I wonder if we can create a chart about this. And I'll ask you to pause the video here and take some time to think about what would be the best chart to display this data, and then actually start to draw that chart. And hopefully you were able to do that. And this is one of the charts that I came up with. I said, well, this is one variable data where I already have a frequency table. Right? I had 1 3, I had 3 4s, I had 6 5s, 10 6s. That's all one variable data. So if you have covered your unit already on one variable data, then you should be able to recognize that, when you have numerical data like this, a column chart would be super useful. So over here, I've got my column chart started. I've got the numbers, the available options down here, 3 through 12. And let me take a look at the frequency to see, how big my y-axis needs to be. I could draw it, and I only need to go up as high as 12, because that's the highest number. So there's my y-axis. And now I just start drawing the column. So my column for the number 3, how often did this come up? Just once. So it'll be a very small column. For number 4, it'll go up to 3. For number 5, it'll go up to 6. Number 6 will go all the way up to 10. For number 7, I can go all the way up to 12. And then this, similarly, I just keep going down the chart, and I keep making columns whose height matches the frequency from my frequency table. So taking a look at this is my column chart. How might this help us understand probability better? And what do you notice about this chart? Take just 2 minutes here to take a look at it, pause this video, and see what do you notice, and what does this help us understand about probabilities? The first thing that might be immediately obvious is the gap between some of these numbers. Looking at the numbers themselves, these percentages, you might say, oh, these seem pretty similar, right? These are like really small numbers. All of them are percentages. But when we look at the actual graph here, we can see, oh my gosh, the difference between 3 and 7 is huge. This is so many more times likely, you are so many more times likely to roll a 7 than you are to roll a 3. Even though it seems like, oh, it's just like a 17% chance more, between 1 and 18. That's certainly not true. It's 17 percentage points, but it seems way, way, way more likely that you are going to roll a 7 than a 3 once we have it visualized in this way. The other thing you might notice, especially if you've covered that one variable data unit, is that this looks like a normal distribution. And you would be absolutely correct. This is exactly a normal distribution. 68% of the data is within one standard deviation. So you are really, really likely to roll a number between 6 and 9. That 68% of your rolls will be between 6 and 9. 95% of your rolls will be between 4 and 11. And it's really, really rare that you'll roll a 3 or a 12. So using a column chart to visualize our data helps us understand, and get an idea of really how much more likely it is that one number will roll more than the other. But it also helps us realize that the numbers in the middle are the numbers that will roll the most frequently. And the further we get from the mean of this data, and the mean would be 7.5, the further we get from the number 7.5, the less likely it is that we are going to roll that number. The other sort of graph that you may have used to describe your data is a pie chart or a circle graph. Now this is a pie chart. I made it quite easily using spreadsheet software. I just put in all of my numbers, my frequency table, and then I said insert chart. And that made it really easy for me to create a chart without much trouble. And notice that it's put in all of my values here. So this is the 9. There's a 16% chance of rolling a 9. It's rounded these numbers a little bit, but that's okay. How does this circle chart help me understand these probabilities in a way that the column chart doesn't? Or in other words, what do you notice about this circle chart that would help you out here? Take 2 minutes, pause this video, and then hopefully you've noticed some of the same things that I have. So one thing that is sort of that you might have noticed that's sort of related to the column chart actually is look at the way that this pie chart is divided. It's almost, actually it is, isn't it? It's symmetrical. The numbers, the slices on the left are exactly the same size as the slices on the right. It's almost like this has a mirror image cut right down the center. And that helps us realize that yes, even if our mean is 7.5, the mean would be 7.5, and as we get further away from 7.5 towards the right, counterclockwise, or even clockwise along the left, we notice the slices getting smaller and smaller. And therefore, we can see that, yes, 12 and 3, the further we get from our mean of 7.5, the less likely those numbers are to roll. Also similar to the column chart, you could see how big the slices for 7 and 8 are compared to 12 and 3. Now, it's my personal opinion, you may feel differently about this, but I feel like the column chart does a better job of showing how big the difference between 7 is compared to 3. Because the pie chart, they're kind of far away, and it's tough to tell, okay, hey, is 7 the same size as 6? Is it a little bit smaller? It's a little bit tough to tell looking at a pie chart. We could, of course, look at the numbers to notice that, yes, 7 is 19% and 6 is 16%. But it's tough to tell just from looking at it. So from that respect, the pie chart is a little bit worse. Finally, similar to a column chart, the size of the slices are obviously telling us how likely one of these are to roll compared to the others. But what's different about a pie chart, something that the pie chart offers us that the column chart does not, is it represents to us that these numbers are all of the possibilities. The circle is totally full. There's no more space for any other possibilities. There's no space for any of these probabilities to increase. For one of them to increase, another one has to decrease in order for this to still be one full circle. Whereas with a column chart, the columns could keep increasing in size forever and ever and ever. And so a circle chart or a pie chart is really useful for reminding us that these make up a whole, that all the probabilities together create that will fill up the entire probability space, and there will be no room left over for any other possible outcomes. For example, there's no way I could roll a 13. There's no room in here for a slice of 13 to fit. Even if it was only 1%, there's no room for even 1% to fit. These will all add up to 100%. I could not increase the chances of rolling an 8 from 19% to 25%. There's no room for that extra 6% without one of the other probabilities, one of the other outcomes, getting reduced by a total of 6%. So if I want to increase one of my possible outcomes likelihoods, I have to decrease the others, and the pie chart reminds us of that. And that's really what this lesson is all about, theoretical probability. You can calculate the theoretical probability of something that has multiple trials in it or multiple steps by using a tree diagram. What is theoretical probability? It's a measure of how likely an event is to happen. And the way we calculate the exact theoretical probability is by counting the number of successful outcomes and dividing that by the total possible outcomes, however many there are. Your answer when you divide these will be a value between 0 and 1, and that's as a decimal, or between 0% and 100%, and that's as a percentage. If you want to find the probability of one of several different events, so perhaps you want to know, okay, I want to know if I want to roll, like what's the chances I could roll a 7 or an 8? What's the chances I roll a number greater than 9, so 10, 11, or 12? So these are one of several events. So that is several different events, a 10 or an 11 or a 12. And to find that out, we would just add the individual probabilities for 10, 11, and 12 all together. To find the total number of outcomes in a series of steps, so when rolling 3d4, there were 3 steps. To find the total number of outcomes, we just multiply the number of outcomes in each step. So rolling a 4-sided dice has 4 outcomes. And if we're doing that 3 times, we did 4 times 4 times 4 to get 64. And one thing to remember is something called the complement of an event. The complement of an event is the likelihood that it will not happen. And the way we would calculate that is we subtract that event's probability from 1. Or if we're using percentages, we would subtract it from 100%. So just to give you a quick example of that, if something has a 25% chance of happening, its complement, the likelihood that it will not happen, that would be 75%. 100% minus 25%. Let's do an example here. What are the chances of having 3 boys in a family of 5 children? So this is a bit of a tough question. So I would say that you maybe need to pause this video and think about this for maybe 10, even 15 minutes to see if you can come up with some sort of answer. Now, when you come up with your answer, you may be tempted to just go 3 divided by 5. But if you do that, that would tell me that maybe you don't quite understand that there's 3 successful outcomes is not what we're looking for. A successful outcome is a combination of 5 children that has 3 boys. So I want you to imagine all of the different things that could have happened in this family. For example, this family when they had their first child, there were 2 possible outcomes. That child could have been a boy or could have been a girl. And if one of these were true, when the parents had their second child, again that was 2 outcomes. And this is sort of just like flipping that coin, right? Getting heads or tails. What were the chances of getting heads once and tails once? When we did that, we saw that we had to start drawing a tree diagram. And so the second possibility, if the first child was a boy, the second child could be a boy or a girl. If the first child was a girl, those same 2 possibilities exist. And just like flipping that heads or tails coin 2 times created 4 different outcomes. Remember, 2 heads, heads, tails, tails, heads, tails, tails. This would also, just having 2 children creates 4 outcomes. 2 times 2 is 4. And so we've got the 4 outcomes are boy, 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 girl, girl, boy, or girl, girl. Those are 4 different things that could have happened so far. Not just 2 kids. What if they have a 3rd kid? Each of these situations will be split up into 2 more possible futures, a boy or a girl, for each of the 4 situations. So we had 4, now we have to multiply that by 2 again to get 8 situations. And this is what I mean when I say you have to multiply the number of outcomes in each step to find out the new number of total possible outcomes. The 4th child would create 2 more, and the 5th child would create 2 more than that. And you can see how complex this starts to get once we, have more and more steps involved. So just to give you an idea of exactly what's happening here, suppose we were looking at this, each of these end points of this branch represents a different outcome. Suppose we were looking at this outcome right here. Let's trace the branch back. This would mean having a boy, then a girl, then 2 boys, and then a girl. That's one outcome. And that would be an outcome that has 3 boys. But there's lots more. Let's go through this entire tree diagram and see which of these has 3 boys in it. Starting off here, boy, 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 that's 3 already, which means having a 4th boy would instantly be not a successful outcome. Boy, 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 then we need to have 2 girls. So this would be the first successful outcome. Boy, 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 girl, girl. That's 3 boys in a family of 5. Now, you could have started off this question just by, starting to write down combinations like this. Boy, 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 girl. Boy, 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 girl, girl, and so on, and you would have found a total of 6 combinations, girl, 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 a total of 6 different combinations, and you might say, oh, those are the only things that can happen. But we see here when we make a tree diagram that there are actually 32 different combinations that can happen, and these are just the different, the word is called permutations. There are 6 different permutations, I believe, but 32 different combinations. So let's just go back to looking at our tree diagram and seeing what are the other combinations we can find. So here is one of them. I'm going to invite you to pause this video for 2 minutes and see if you can find out all of the different combinations that would result in having 3 boys. By making a tree diagram like this, hopefully you've had a chance to see how many different combinations there are, and I'll certainly take that up here. But by making a tree diagram like this, we've helped ourselves out because we've done it in a way that's really organized. We have made it so that we just sort of have to go from left to right, and we know, we will see very easily, whether or not there are 3 boys. For example, I knew I did not have to go down this branch because I already had 3 boys, so I knew the next 2 have to be girls. And then I'll just go left to right. So the first time I made like I ended up here, and this was the only path I could go. So these 3 are not options. So instead of taking this path, I'm going to take this path now. Boy, boy, girl. Okay, I have 2 boys, so I could have 1 more boy. If I have a boy, then my last child would have to be a girl. So that would be boy, boy, girl, boy, girl. That's 1 more combination. And then if I went boy, boy, girl, and instead of going down here, remember I need 1 more boy. If I went down this way and had a girl, then my last child would have to be a boy. And so that's boy, boy, girl, girl, boy. Those are 3 combinations so far. By being this systematic about counting my combinations, I am ensuring that I will never leave one out by mistake. So let's keep going. Boy, girl, boy, boy, girl, right? That's 3 boys. Boy, girl, boy, that's 2 so far. I could have 1 more. What if I have a girl and then a boy? That's another combination. What if I had boy, girl, girl? Then I could have 2 more boys. In fact, I must have 2 more boys to get to 3. So that would be boy and boy. These are 6 combinations so far if I had a boy first. What if I had a girl first? I could go girl, boy, 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 girl. I could go girl, boy, boy, girl, boy. I could go girl, boy, let's see, that's 1 boy, then girl, that's still 1, so I need 2 more boys. I need both of these, boy, boy. So because I needed 2 more boys, this option was not an option. I know I'm done with this branch entirely. I can go over here. Girl, girl. If I have 2 girls and I can have only 3 more chances for kids, then all 3 would need to be boys. Girl, girl, boy, boy, boy. And therefore, having another girl is not an option at any of the branches, so I know that I am done. How many combinations do I have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 out of how many combinations are there here? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 10 combinations out of 32 give me a result of 3 boys exactly. And 10 divided by 32 times 100 would give me 31.25%. So that is the likelihood that I will have 3 boys in a family of 5 children. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.